So this is ELC131, Circuit Analysis 1, and the topic of this video is Thevenin's theorem. Thevenin's theorem states that any linear electrical network consisting of voltage sources, current sources, and resistances can be replaced with an equivalent circuit consisting of a voltage source and a series resistance, as shown in the circuit of Figure 1. Now, the steps to deriving the Thevenin equivalent circuit are: 1. To find the Thevenin equivalent voltage, VTH. And this is the voltage across the terminals A and B with those terminals A and B opened. Step 2 is to find the Thevenin equivalent resistance, RTH. And this is the resistance between the terminals A and B, with all voltage sources replaced by a short circuit and all current sources replaced by an open circuit. Step 3, we connect the Thevenin voltage and the Thevenin resistance in series with the terminals A and B. This is the Thevenin equivalent circuit as we saw in Figure 1. Then we replace the component or components that were originally connected to the terminals A and B. Now in this video we'll look at a couple of examples or applications of Thevenin's theorem where we only have a single resistance connected across these terminals A and B. However, understand that there could be many components or even a sub-circuit connected to terminals A and B. And these components could include capacitors, diodes, transistors, the list goes on and on. But it gives us a way to reduce a complex circuit step by step by taking a group of components and replacing them with a single voltage source and a single resistance. So let's look at an example. The circuit of Figure 2 is a simple series parallel circuit with a resistor RL connected between terminals A and B. And we're going to derive the Thevenin equivalent circuit for the terminals A and B in that circuit. Now, we'll also use the terminology that we are finding the Thevenin equivalent circuit as seen by RL. And then we're going to use this Thevenin equivalent circuit to find the voltage across RL. So, step 1 is to find the open circuit voltage across the terminals A and B. Now note, with the terminals A and B opened, there's only one path for current in this circuit, that the source voltage only sees resistor R1 and R2 in series. And whatever voltage we have dropped across resistor R2 will also be seen from the terminals or across the terminals A and B. So our Thevenin voltage is equal to the voltage across R2, which of course can be calculated using the voltage divider formula, V source times R2 over R1 plus R2, which is 6 volts. Now, step 2 is to find the resistance between the terminals A and B, with V source replaced with a short circuit. Now, if we look at the circuit, that to get from A to B, I can take two paths. One would be through R2, and one path would be through R1. So with respect to the terminals A and B, resistors R1 and R2 are in parallel. So the Thevenin resistance is equal to the parallel resistance of R1 and R2. We can calculate that using the product over sum, R1 times R2 divided by R1 plus R2, which gives us a value of 1.1 k ohm. Now that we have found VTH and RTH, we connect those two in series with terminals A and B. And then we replace whatever component or components were originally connected between or across terminals A and B. So the circuit of figure 5 shows us the equivalent circuit of the circuit of figure 2 with respect to terminals A and B, or as we said earlier, as seen by the resistor RL. And of course, with this Thevenin equivalent circuit, we can calculate the voltage across RL using the voltage divider formula, VTH times RL over RTH plus RL, 5.41 volts. Now, I'm sure that a lot of you are thinking this sure was a lot of work. We could have just analyzed the circuit of figure 2 much more quickly. However, the benefit of deriving the Thevenin equivalent circuit is that if we want to see how this circuit reacts or performs if RL was 9 k ohms, after I've derived the Thevenin equivalent circuit, all I have to do is change the value of RL in the voltage divider equation, and I can easily calculate the load voltage. Whereas if I wanted to find the load voltage for a load resistance value of 9 k ohms in the circuit of figure 2, I would have to determine R2 in parallel with R load in series with R1 to find the current, to find the voltage. And again, if I want to see how this circuit performs or acts with different values of R load, it's much, much simpler to derive the Thevenin equivalent circuit so that I can change R load in just one equation. Now let's look at another example or application of Thevenin's theorem. And we look at the circuit of figure 6, and I hope you can recognize this as being an unbalanced Wheatstone bridge circuit. And when we discussed Wheatstone bridges, we said that we could not reduce and therefore analyze an unbalanced Wheatstone bridge because there's more than one current flowing through the resistors R2 and or R4. However, we can use Thevenin's theorem to analyze this circuit. So what we're going to do is derive the Thevenin equivalent circuit for the terminals A and B in the circuit of figure 6. And again, we also state this as finding the Thevenin equivalent circuit as seen by RL. And then we're going to use the Thevenin equivalent circuit to find the voltage across RL. So step 1 is to find the open circuit voltage across the terminals A and B. And notice with terminals A and B opened, we see resistor R1 and R2 in series. Whatever current flows through R1 can only flow through R2. And of course, with the terminals A and B open, we see resistor R3 is in series with resistor R4. And of course, the Thevenin voltage is the voltage from A to B. So if we look from terminal A to terminal B, we find a voltage drop across R2, positive to negative. and we find a voltage drop across R4 that is negative to positive. So the Thevenin voltage, the voltage from A to B, equals VR2 minus VR4. Now, we actually could have gone the northern route. We could have gone from A to B through R1 and R3, which would have given us, oops, that's not right. Which would have given us minus VR1 plus VR3, but the values will be the same regardless of which direction we take, because if I go all the way around this loop, the voltages have to add up to 0. So we can calculate the voltage at node A, which again equals VR2 using the voltage divider formula, V source times R2 over R1 plus R2, which gives us 9.84 volts. And the voltage at node B equals VR4, which can be calculated again using the voltage divider formula, V source times R4 over R3 plus R4. So the voltage at node B is 10.1 volts. Therefore, the Thevenin voltage, again, is the voltage from A to B, which is 9.84 volts minus 10.1 volts, which gives us negative 260 millivolts. Now, step 2 is to find the resistance between terminals A and B with V source replaced with a short circuit. And this is shown in the circuit of figure 8. Now, it's difficult for you to visualize the relationship of the resistors in the circuit of figure 8. So I've redrawn the circuit of figure 8 and in figure 9. And figure 9 shows us, of course, that from A to B, we see resistors R1 and R2 in parallel, and resistors R3 and R4 in parallel. And these parallel groups are in series. So to get from A to B, I can either go through R2, or I can go through R1. R1 and R2 are in parallel. And to continue on to point B, I can either go through R4 or I can go through R3. So resistors R3 and R4 are in parallel. And again, the parallel combination of R1 and R2 is in series with the parallel combination of R3 and R4. So the Thevenin resistance is R1 times R2 over R1 plus R2 plus R3 times R4 over R3 plus R4, again using the product over sum formula to find a parallel resistance. So we get a calculated value of 3.66 k ohms for the Thevenin resistance. So we then place V Thevenin and R Thevenin in series with the terminals A and B and connect the component or components that were originally connected to those terminals. So figure 10 shows us the Thevenin equivalent circuit of the circuit of figure 6, again with respect to terminals A and B, or as seen by RL. And we can use the voltage divider, equation to find the voltage across the load resistor, VTH times RL over RTH plus RL. Again, note the polarity of the voltage source VTH with respect to the terminals A and B, that VTH is negative with respect to terminals A and B. So we calculate the load voltage, the voltage across RL, at negative 190 millivolts. Now, of all the circuit analysis theorems that we'll discuss this week, Thevenin's is the one that is most often used. So the concept of Thevenin voltage, the concept of Thevenin resistance will be used again and again in courses throughout the entire 2 years of the degree program, as well as used or referenced in industry. So you need to be familiar with, comfortable with the concepts of Thevenin's equivalent circuits, because again, these ideas will come up again and again in different circuit analysis applications.